Okay, guys. So I want to go through a little example in section 16.9. So we're going to talk about a problem that's in the divergence theorem section. And this problem asks us to use the divergence theorem to evaluate a surface integral where S is the sphere, yada, yada. So we're asked to calculate a surface integral. And the problem is that the divergence theorem doesn't quite apply to these. So here's my issue. The divergence theorem says this. It says that if I double integrate over a surface of vector field d surface, right, that this is the same thing as triple integrating over the inside of the surface. So that's just going to be the unit ball instead of the unit sphere, right? So the unit sphere is just the skin. That's my surface. The unit ball is the stuff inside the sphere. So we're going to triple integrate over the unit ball the divergence of our vector field d volume. And now the problem I have here is this kind of mismatch, which is that I don't have either one of these. And so it's hard for me to imagine using the divergence theorem in this way. So here's my thought. I'm going to try to make one of them fit. And so what I'm going to do is I'm going to take this thing and I'm going to look at it and say, okay, I have this sneaking suspicion that this ought to be some kind of normal vector to the surface. And I've done a couple of spheres. So I think that I remember that if we make S of theta and phi, that we could parameterize the unit sphere by taking cosine theta sine phi, sine theta sine phi, and whoops, I got a little close to the edge there, and a cosine phi. And then I've done some of these problems pretty recently, so I think that I can probably remember what ds ought to be. So I think that I calculated ds as a sine phi and then this stuff, and then a d theta d phi here at the end. And like, okay, well, to me, this stuff is like a vector x, y, z, right? That's just the same as the surface vector. And the thing going on there is when you've got a sphere, right? If you're looking for a normal vector to that sphere, you're looking for a vector that sticks straight out of that surface. And a vector that goes from the inside, from the center, out to the point on the surface is parallel to that. So the sine phi is just kind of some kind of an area distortion, something or other. That's really got to do with the fact that when I kind of draw longitude and latitude lines on this thing, they get smaller up towards the top. Like that's all there is there. So if I calculated the d scalar s here, which if you were in class, I kind of screwed this up. So I want to apologize for that. Whatever, we'll fix it now. So the d scalar s would be the magnitude of this vector. So in my case, that's going to be the magnitude of this whole vector, which is actually just the absolute value of sine phi, because this stuff, the x, y, z, that stuff's on the unit sphere. And then I get a d theta and a d phi here. That's actually just the definition of ds. Had I looked in the book, I maybe would have found that ds is the normal vector and then some kind of d area with respect to the surface, or a unit normal vector, right? I didn't happen to remember that, and so I arrived at it in a slightly different way. That's totally fine. We got here. The important thing is that we get this magnitude of sine phi here, right? And so now I'm like, okay, um, hmm, I I guess that looking at this guy, I'm kind of inclined to think that this guy might actually be the double integral over the surface of x, y, oops. I kind of want to think about x, y, z here. right? And then like a D. Oh shit! I kind of just don't know what to do with this guy. So I'm gonna like half convert, I guess. This isn't a good way to do this. I'm gonna kind of convert to spherical and we'll see what we get. So I'm gonna say, all right. This feels like if I put X, Y, Z here, I should have 2 comma 2 comma Z in here. And then I should have some kind of dotted with X, Y, Z. And then, oh heck, there's some kind of a scalar thing going on here. And I'm like, all right, I think this stuff here ought to end up being that DS thing. So my, I'm just like, huh, where is that going to come from? Like, okay, well, I got some of that though. See the XYZ over there is actually the same as this part that I need in my DS. So I'm thinking, hmm, you know, I bet you that this is the double integral over S of our little 2 Z. And I think we'd have to sort out what Z means. I'm just going to sort out what Z means. I'm going to put in a cosine phi here. So I'm just going to convert this sucker to spherical. So I've got a cosine phi there. Then I've got well, absolute value of sine is really actually just sine in that interval. So I'm like, okay, so then there's a dot x, y, z, and then there's a times a sine phi d theta d phi here. And that's just me converting, right? Oh, except XYZ doesn't really make sense. I really should put that in spherical. So let's do that. So we're going to take this guy and I'm going to put in XYZ in spherical, right? Which is my cosine theta sine phi, sine theta sine phi, and a cosine phi. And then here I've got a times a sine theta d, or sine phi, d theta d phi. Like, okay. All right. Cool. Good. Well, that actually sorts my thing. If I multiply this out and then convert back to X, Y, and Z, I actually have what I started with. And so, yeah, I'm just going to take this arrow and I'm not going to end it there. I'm going to skip this step where I was thinking. And I'm just going to pop straight to, I converted to spherical and I got this. Okay, rad. Now, what's the vector field that I'm actually integrating here? Well, the vector field that I'm actually integrating here is this guy, the 2 cosine phi. And I can just go ahead and calculate the divergence of that. I need to convert it back to Cartesian coordinates to calculate that, but it's not so bad. So I'm thinking by the divergence theorem here, this is actually equal to the triple integral of the divergence of this vector field 2 Z d volume. And then I'm like, okay, but like I can calculate the divergence of that. And this is over the inside of that, right over the ball. So this is the triple integral over the inside of the ball of 1 d volume, because the divergence of that vector field is 1. And as it turns out, this is a lot easier than it could have been. And had I screwed this up, like maybe I would have if you watched this in class today and I lost track of that stupid sign. Um, yeah, here we are. I know what the volume of a sphere is. It's 4/3 pi and the radius is 1. So I get 4/3 pi times 1 cubed. Check, done. End of problem. Had we screwed this up, it would have been really tragic. I'm glad we didn't.